Hello everyone. We're getting ready to start chapter 7 here, which will be our last installment of the trigonometry section. And it kind of follows in with what we did in chapter 5 and 6 as we took different looks at the trig functions. Graphical approach, geometric approach this last chapter. And now what we're going to do is kind of look at the algebraic aspect of trigonometry. We're going to combine trig functions together. We're going to simplify trig expressions, prove identities, factor expressions, solve equations. Everything that you do in an algebra classroom, we're going to do with the trig functions. And so the basic tool of this whole idea of algebra, or trig as algebra, I guess would be the way to say it, are our trig identities. And quite simply, an identity is any equation that holds true for all possible values of the variable. And so in the long run, there's an infinite amount of identities out there. We tend to focus in on a very basic set few and use that small bunch to prove any others that we would like to use. And probably one of our number one, and I guarantee this, our number one trig identity by the end of this chapter is going to be this one right here. Oops. Got to select a pen, right? Holy cow, is that thick. Sine squared x plus cosine squared x equals 1. And we recognize that as a Pythagorean identity. And so no matter what value I put in for x, should make this true. So we can take one of our unit circle values, let's use pi over 4. And put that in. So we'd have, well, it doesn't, commutative property, I'm going to invoke that right here. Doesn't matter what order you add. So cosine squared pi over 4 plus sine squared of pi over 4 should be equal to 1. Now we're going to do all our work on the left side of the equation to see if it comes out to be the right side. Now, pick pi over 4 for a reason, because both sine and cosine are the same at pi over 4, which would be square root of 2 over 2 squared plus square root over 2 over 2 squared should be equal to, well, kind of running out of room vertically here, so let's move laterally. So let's see, square root of 2 over 2 squared. Square root of 2 squared is 2. 2 squared is 4. Plus 2/4 equals 1. And so, right there, that's just an example of one of our more popular trig identities and what the definition means. So there's where it holds true for pi over 4. But we proved in chapter 5 that no matter what value we put in for x, we're going to get a true statement. This next slide here just kind of shows us what we consider in trigonometry are fundamental identities. Now you can see we don't have all the ones that are on our unit circle yet. Those will be covered as we continue on through the chapter. But these are the ones we consider our fundamental ones, our basic, our most basic. Our reciprocal identities are just defined for us. And I'm going to take some time in another presentation to prove the Pythagorean, even and odd, and cofunction identities. We already did Pythagorean and even odd identities in chapter 5, but I would like to go over those again. I think it's important for us to know where these come from and why they're true as we use them to prove other identities. We could treat our trig functions like algebraic expressions. I think everything on the left goes without saying here, except I do notice that we have a little bit of a problem with our exponents. This should be x squared. I gotta change this here. I think I do this. There we go. Okay. Let's go over on the trig side. So we're over here now. So sine of x plus sine of x is 2 times the sine of x. If we're going to multiply trig cosine times cosine, We do have a problem here with our notation. That should be an exponent of 2 there. But I think the more common way to write this is to take our exponent and write it in between the trig function and the variable, cosine squared of x. Both of these are perfectly acceptable ways of writing exponents, though. Tangent, cosine are not like terms, so we would not add them together. They're simplified as possible, and you'll find that we could treat them as common denominators. 3 over the secant of x plus 4 over the secant of x is 7 over the secant of x. If I have 3 over the sine of x plus 4 over the cosine of x, I could add those together. I would need a common denominator of sine of x times cosine of x. And to get that, I would have had to multiply this first fraction by cosine over cosine, so that would leave me in the numerator 3 cosine of x plus, over on the right side fraction, I would have to multiply by sine over sine, and so that's 4 sine of x. Right, and so let me write that a little clearer here. 3 cosine of x plus 4 sine of x all over sine of x times cosine of x. Alright, now you'll see as we continue on quite a bit here. In fact, I'm going to finish off this particular presentation with some examples of simplifying trig expressions. These are expressions because as they start out, you don't see an equal sign. And so here we have the cosine of t plus the tangent of t times the sine of t. Certainly looks like an expression that is probably in its simplest form. But the one thing that has me thinking here is this whole tangent of t. Because it has sine and cosine in it. Alright, and so that's going to leave us with a bunch of sines and cosines. And so I think ultimately what we need to do is look for places where things are going to cancel out, where things are going to simplify for us. And so first thing I'm going to do here is rewrite this, but change that tangent of t into its reciprocal definition. So I'm going to rewrite this whole expression. So I'm going to start with the cosine of t plus, now I'm going to go tangent is sine over cosine times the sine of t. Alright, so now over on the right side here, I'm going to combine this multiplication, so it's going to be plus sine squared t over cosine of t. Remember, we treat that as being over 1. Sine times sine is sine squared. Cosine times 1 is cosine of t. Over here on the left, I didn't do anything with it right away. I'm going to bring down my equal sign here. But if I need, it looks like I have to do an addition here. I have a fraction over here on the right. So if I'm going to make a fraction with the common denominator, that common denominator needs to be cosine of t. And so in other words, what I did here was I multiplied this by cosine over cosine. Kind of running out of room here, but so just see what we're doing here. Cosine over cosine times cosine over 1. Cosine times cosine is cosine squared t. And cosine times 1 is cosine. And so now we can combine this into just one expression. And I think you're going to find that anytime you see an addition, we try and get it into, or subtraction for that matter, into a single fraction. And so common denominator says we're going to have cosine of t on the bottom, and top becomes something we should recognize. And so this is key here. We are always looking to simplify. And so rather than keeping this as cosine squared plus sine squared, we know that our Pythagorean identity says that this is equal to 1. So we have 1 over the cosine of t, which by its reciprocal definition is the secant of t. And so what we did right here was took something that didn't look like it was necessarily simplifiable and certainly got it down into a single trig function, which to me is much more simple than what we started out as. All right, so there is a benefit for us in terms of why we would want to simplify. Why deal with trig functions when it could be represented by a single? Now, don't get me wrong, not everything's going to be quite that simple or work out that easy. Alright, let's take a look at one more here. So if I go with sine of theta over cosine theta plus cosine theta over 1 plus the sine of theta. Alright, I thought I had this written in here already, but I guess not. Okay, once again we have an addition of fractions. So instantly looking for common denominators, and what I see here is we got cosine theta on the left, 1 plus sine theta on the right, and so our common denominator is going to be a multiplication of those two. And so on the right here, I'm going to multiply this to get my common denominator by cosine of theta over cosine of theta. On the left, it's going to be 1 plus sine of theta. Boy, those eyes are tough. Over 1 plus sine of theta. Remember, there's a multiplication here. Maybe I need to do that x instead of raised dot because it's not coming out very good. Alright, what do we have here now? Let's put an equal sign. Anytime you're doing identities, you need to link steps through equal signs. And so up on top, you know, we have to realize that this is a whole expression. Distribute that sign, so you have sine theta plus sine squared theta. Remember, this is all going to be over our common denominator of cosine theta times the quantity 1 plus sine theta. Alright. Now let's go back up to here. So there's our left side multiplication plus cosine times cosine is cosine squared theta. Alright, now at this point right here, we should recognize, once again, our Pythagorean identity. And so this is equal to 1 right here. So if I rewrite this, I can rewrite it as the sine of theta plus 1. Replace the sine squared plus cosine squared with the 1 over cosine theta times 1 plus sine theta. And when you look at the top and bottom, can we cancel out that sine theta plus 1 with 1 plus sine theta? Absolutely. Order doesn't matter when you add. And so commutative property says that those are equivalent. They're factors. They're multiplications. So absolutely. And so what are we left with after that cancellation? Numerator's left with 1 over the cosine of theta, which ends up being 1 over cosine theta is defined as the secant of theta. Now it just happens that the two we looked at ended the same at secant theta, so don't start thinking that they're all going to end that way. Hopefully you have success with simplifying expressions, and if not, make sure you're asking your questions.